All right, what we're going to be doing is looking at the idea of relative motion. So we're going to start off by a really simple example of relative velocity. So we have a person standing on the ground, and so he's just standing there, he's still. There's a truck that's moving with the speed of 15 meters per second, and then the guy in the back of the truck, obviously this is not recommended, it's not safe, is throwing the ball horizontally with the speed of 8 meters per second. So the question would be, how fast does this guy see the ball go? And you probably would just add 8 plus 15 and say 23 meters per second, because you know the truck's makes this guy go 15 meters per second, then he throws the ball, and the ball's already moving with the speed of the man, so that's, you simply add those together. The reason that all these speeds are different, the reason that this guy sees the ball move at a different speed than this guy, has to do with the idea of the frame of reference. The frame of reference sounds all fancy, but all it means is it's basically, what are you measuring everything relative to? Are you measuring something relative to the truck, or are you measuring it relative to the ground? And this is what we're looking at with relative velocity. So when we look at this, when we want to find the speed of the ball with respect to the ground, what we did was we took the velocity of the truck with respect to the ground and added to it the velocity of the ball with respect to the truck. And so that's how we got that value. So we want to be able to work with this a little bit more, and so we probably have to look at it in a little bit more detail, but let's think about one more thing. What if the person in the truck threw the ball straight up? So here's the truck, here's the guy, he throws the ball straight up, and here's the guy on the ground. Now you want to know what would he see. Now remember, the velocity of the truck with respect to the ground was 15 meters per second. Now, if you might be able to think this through. If you were the man in the truck, you might see the ball simply go up and then come back down. But if you're the guy on the ground, as the ball's going up, it's moving up, but it's also moving horizontally with the speed of the truck. So what happens is you see the ball go up, but it's also moving horizontally. In fact, this is like projectile motion. And so you're simply adding the velocity of the ball with respect to the truck plus the velocity of the truck with respect to the ground gives the result of what the person sees it move with respect to the ground. So we're still simply adding those velocities, but notice that there's a vector nature to it. And that's what we want to understand more, because we're not going to simply do problems all the time with relative velocity where the objects are just all moving in a straight line. We might look at something like trying to swim across a river, but the river's flowing, so you end up swimming in a diagonal line instead of going straight across. So we're talking about moving frames of reference and how velocities depend on how the velocities are determined when you're moving in different frames of reference. So we're going to start off with this picture. This is a picture from your book, and it might be kind of confusing, but this is your moving frame of reference. So this could be like, you could think of this as your truck. And then this is your stationary. frame of reference. So the axes that have primes on them are moving, and the ones that don't have primes on them are stationary. Now we start off, first of all, just locating a point, and we have actually two sets of coordinate axes. We have the unprimed, the stationary ones, and the primed. And notice the position of point P relative to our stationary frame of reference, that's this vector right here, is equal to the position of the object in the moving frame of reference plus the vector that goes between the stationary frame of reference and the moving frame of reference. And so this is the vector that talks about the distance between them. Now, that's nice, and we can kind of see how those two vectors add together. This vector and this one add up to give us this one. So it all makes sense. But we're not that interested in it, but what we're more interested in is these velocities. So we want to take the time derivative of these expressions. And so this would give us the velocity of P in the stationary frame of reference is equal to the velocity of P in the moving frame of reference plus the velocity of the frame of reference, the moving frame of reference with respect to the second one. So again, this kind of plays the role of the truck. This is the ball in the truck. And this is the ball relative to the ground. It might seem really confusing how we tell the difference, but let's just take a look at it here. Here's a train moving and someone walking in the train, and the cyclist is watching from a stationary frame of reference. So we see how fast this person, the passenger, is moving in the train, but we want to know how fast does it seem like she's moving relative to the person who's stationary, and that would be the cyclist. Go ahead a little. If we use this notation, I find this really helpful. So if you kind of think about how the subscripts kind of go together, like here, this is the velocity relative to the train, and the train relative to the earth. So this is for the picture back before. And so here, this is the velocity of the train with respect to the earth, and this is the velocity of the passenger with respect to the train. And when we add those two together, we get the velocity of the passenger with respect to the earth. And notice when we look at these subscripts, you can kind of imagine like the T's kind of cancel out. We get passenger with respect to the train and velocity of train with respect to the earth. We could think of those as canceling out, and what we're left with is the passenger with respect to the earth. I find that method really helpful in trying to remember how to add them together properly, so hopefully that'll be helpful to you. And if we think about it, so this is the velocity of the train with respect to the earth, and this is the velocity of the passenger with respect to the train. When we add those two together, this is what it looks like the passenger does according to the bicyclist, and that seems to make sense if you think about it, because the bicyclist will see the passenger moving with the speed of the train, which is in one direction, and then also moving perpendicular to that with her own speed, and then the result is the two added together. So here is a problem where we would try to use that information. So we're told that the velocity of the airplane wants to move with an airspeed of 200 kilometers per hour and to fly due west. So they're flying due west, and so that's the velocity of the plane with respect to the earth is the 200 kilometers per hour. Oh, no, I'm sorry. Let me erase that. Let me just get rid of that. So the pilot wants to end up going due west, but there's a wind blowing from the north. So that's the velocity of the wind with respect to the Earth. And what's going to happen is the pilot, he wants to end up going like this, the velocity of the plane with respect to the Earth. This is what's desired. So if you think about it, he's going to have to sort of fly up a little bit north because he's going to get blown down when he's all set, when he's in the air because of the wind. So this is the velocity of the plane with respect to the wind. So if we add the velocity of the plane with respect to the wind plus the velocity of the wind with respect to the Earth, we're left with the velocity of the plane with respect to the Earth. Now, if we think about this, in the end, this is only in the west direction. So we know that the y components add up to be 0 because it doesn't go north or south. So the velocity of the plane with respect to the Earth in the y direction is 0, which is equal to the velocity of the plane with respect to the wind times the sine of that angle which we're looking for minus the velocity of the wind with respect to the Earth. And so we could use this to try to figure something out. So we know the velocity of the plane with respect to the wind times the sine of theta is equal to the velocity of the wind with respect to the Earth. And that's actually 120 kilometers per hour. And this is 200. So we can figure out our angle is, the angle whose sine is 120 over 200. So if we take the inverse cosine, we get 36.9 degrees. So that's the angle that the plane is going to fly at. So we know that. And so then if we know the velocity of the plane with respect to the Earth in the x direction is going to be the velocity of the plane with respect to the wind times the cosine of that angle. So that was 200 times the cosine of 36.9 degrees. And so that gives us an answer of 160 kilometers per hour. And so that is an example and a little bit about doing relative velocity. So hopefully that's somewhat helpful.